Okay, here's another example. I didn't put it in my notes. I think I took it out of my notes because it's a difficult example. It comes out of the Meriam and Kraige book of my second edition. This is the book that I used in undergraduate dynamics. A more up-to-date, I think this is the 7th edition. You can see this is the sample problem where the freighter is moving at 8 knots when its engines are suddenly stopped, and it takes 10 minutes for the freighter to reduce its speed to 4 knots. All right, so these are things that you could actually measure. So that's one of the reasons why I kind of liked this example. But it is something that is like not necessarily intuitive. You have to go through a couple different steps to be able to get here. And determine and plot the distance s in nautical miles moved by the ship and its speed in knots as functions of time during this interval. The deceleration of the ship is proportional to the square of its speed. And this is actually true. That's actually something that is known. And proportional with some constant right there. So it's proportional negative because it's decelerating, and some unknown constant times the velocity squared, right? So I don't know if I wrote it out differently. If it takes 10 minutes for the freighter to reduce its speed, determine the distance x in nautical miles moved by the ship. Okay, so they're asking for it slightly differently right there. So let me write this thing out in the way that I would right here. Okay, so this is difficult example. And the given, at least from the one that I'm doing right here, is that acceleration is in this form right here, right? And that we know that the initial velocity or speed is 8 knots. Now we're going to need to know, we might need to know the conversion. Did I have to use the conversion? I don't think I used the conversion. You can convert this into miles per hour. These are nautical miles per hour. That's what a knot is. So weird type of thing. And we know that, okay, so that's at time equals 0, right? At time equals 10 minutes, all right, the V is now going to be at 4 knots. And I decided to go non-cursive there for some reason. Which, by the way, that's going to be this is 60 hours, right? With too many S's. Wow, really doing a great job there. Really good. Okay. So, what we want to do here is we want to use case 3 because acceleration is a function of velocity. But we're dealing with time rather than position right here. So let's go ahead and take this relationship and move it over and get time there, and then take 1 over the acceleration and dv, right? And then integrate these things. All right, so so the integral of time right here, starting from beginning to t, is going to go from 8 knots to v, and we're going to divide by negative k v squared dv, right? So what we could do is we could bring that k over to the other side. That's going to help us. And so what we're going to find is we get a negative k and t going from 0 to t. It's going to be equal to, and taking the integral of 1 over v squared, we end up finding that we have 1 over v. Is that true? 1 over v squared. Yes, yes, because that's the same thing as having that right there, right? And so you add to the thing. Yes. Okay. So, and that's going to go from 8 to V. So if you plug these things in, you get negative KT is equal to negative 1 over V plus. So I'm wondering about that negative right there. That should there be a negative right here? I kind of think there should be. We move the negative from here, but when we, and I placed him over there, but when we do this guy right here, should we have a negative? I think there should be a negative right there. Yeah. And then that should be 1/8. We put the V in there, and then we subtract out the 8, so that's where we get the positive. Okay. So now what we could do is we know we're given at this time right here. Yes, and I want to use hours because this is this is a nautical mile. They go nautical mile per hour, right? Right, so that's why we want to go for 10/16 hours when we put the thing in there for the K. And so the K here, rewriting this thing out by putting all this in there and solving for the thing, I kept my negatives in there. Here's my 1/4. I'm putting 4 in there for the 4 knots, and plus 1/8, and dividing, and now I'm going to go 10/60s. We end up finding that this ends up being 3/4, 0.75, right? And then if I plug that back into, what am I plugging it back into for my velocity? I'm trying to find this somewhere. Oh, if I plug that back into this right up here and do some manipulation, I get the velocity is equal to 8 divided by 6t plus 1, right? So I skipped over. I don't like skipping over, but I skipped over the algebra. So now this is velocity is a function of time. Which is just good, right? So if I have velocity as a function of time, but now I want to get, I didn't write down what my finds were, right? I did it again. Find. What do we want to find? Determine the distance. Find delta x. Is that right? So we want to find position. Right? We want to find the amount of the distance it has moved. So let's take velocity and go dx dt with it right here. So we have dx is equal to v dt, and we can integrate, we can substitute that velocity back into there because now velocity is a function of time. And I've written down my page that it's a function of position, but I think it's a function of time. Okay, and so the integral dx taken from 0 to x is going to be equal to the integral from 0 to some time of 8 over 6t plus 1 dt. And what we end up finding is that x is equal to 4/3 natural log of 6t plus 1. Right? And then once again, I must have got that from the integration table. Let's see, we have the integration tables up here. I have yes, right there. Okay, so what I do is I take I have the form of the variable right here on the bottom, and then I have the natural log of this right here, but I have to divide by this. Okay, so that's where I get that 4/3, and that's 6t plus 1 right from there. Although that 4/3 has me just a little bit, okay, because it's the 8, right? So that 8 needs to come out to the side right here, and we divide by 6. That's why that's 4/3. Okay. So there's our answer right in here. We could go at t is equal to 10/60th hours. At that time, we can find that the position is 0.924 nautical miles. And so that's the answer. Now let's go back and take a look and see what the book did right here. Okay, so here is the book, and they went ahead and they popped the thing around, integrated it, and we're able to get this velocity is equal to 8 over 1 plus 8 kt, right? And then they went ahead and they put in the knowns of the 4 knots and the 1/6 of an hour, and you see that they got their K from that, and then they were able to write out the same thing. So it looks a little different, but it's just really the same thing that got done. And in this one, they wanted us to graph some things, which is a good idea. The distance is obtained by substituting the expression for velocity into the definition of, there you go, and they're using s instead of x for here, and integrating, and you can see here's where we get the position as it relates to time, and then they go ahead and they stick that back in there. Here we go to the 0.924. So it looks a lot simpler when they do it, but I tried to give more sort of my mindset as I worked through the thing. So there you go. There's another example. It's a much more difficult one.